So my project has been to build a model that can describe globular clusters that includes these potential escapers, which we've heard a little bit about, but I'm going to talk a little bit more detail. But I want to first just say, I worked with Heggie and Varri, who, is this camera on? Yes. Yeah. I just want to say thank you so much. And then not only did I learn a whole lot about something that I've never even thought about before, but you also made it incredibly interesting and fun. Thank you. Okay, so let's get started. So we're going to go way back to things that we learned way back in the age of the dinosaurs, which is the restricted free body problem. And this here, we've all seen this before, but I just want to throw it up again as a starting point. This is the effective potential for a large body with a smaller body or a less massive body orbiting around it in the frame rotating with a smaller body. And these lines of equipotential are a way, is a way of thinking about it in terms of energy. So these are minima, these are maxima in the effective potential, and then there's, we don't care about that one. These two are saddle points right here. And there's the two saddle points, those Lagrange points, are joined by a line of equipotential, which you can think about as being a threshold energy. Stars that have more energy that are inside this cluster, or outside actually either, but we only care about what's in here. Stars that have more energy than this line of equipotential can escape, and they do that through these Lagrange points, which we've heard about through Ben's talk and a few other talks, and we will again later on today. But if you imagine taking this, and you just take a slice right through here and flip it up on its side, so that we're looking at the dimension going into the page, then you can imagine that these two bumps right here are the bumps of the effective potential, where these are the two Lagrange points. And this energy right here, if energy is in the vertical axis, and this is radius in the horizontal axis, that these two, the peak of these two bumps is that energy over which if a star has an energy greater than that, then it should escape the cluster. Stars with energy less than this are bound. However, there are some stars, as explored by Anon, and I'll talk a little bit more about this in a second, but there are some stars that have an energy greater than this critical energy, or this is what I call utidal, that are within the tidal radius and also have stable orbits around the center of the globular cluster, which is marked by this vertical dashed line right there. Okay, so now I've introduced what a potential escaper is in theory, right? But what I'm interested in doing is building a model that includes those for a globular cluster. So what do I mean by a model? Well, I'm talking about a snapshot model, and this is a time-independent way of approaching a description of the observed properties of a globular cluster. So the point of it being is that what I'd like to do is be able to derive some sort of distribution function that through which we can get density, which should have characteristics of a globular cluster, like the core and the tidal radius, the truncation radius, as well as the velocity dispersion and other things you can derive from the moments of the distribution function. And there have been several rather successful models of globular clusters that use a distribution function that's solely a function of the energy of the globular cluster. And these are Woolley and Dickens did one that's called the Woolley model, which makes me feel kind of sad for Dickens. And then there's King and Wilson. These are the most commonly used. And what they do is they write a distribution function that describes the bound stars, meaning stars with an energy less than some critical energy. And then any star that has an energy greater than that, there's no distribution. Distribution function equals 0. Which effectively means then that they aren't including these potential escapers. So top here, I have the surface brightness, and then here I have the velocity dispersion of this is Omega Centauri, I guess. And then on the left, this is a log. This is radial going this direction. This is log. This is linear. That's the difference between the two. And the King and the Wilson models fit these fairly well, fit these profiles fairly well. There is a little bit of a flattening out here at large velocity dispersion, which Felipe was going to talk about later on this morning. But the point of this is just to say, you know, the King and the Wilson models are really not so bad. They do a good job. However, there are some things, some observational evidence and also numerical simulations that point toward a need to go a little bit further. So in the outskirts here, what we're looking at, here's the data, and then this is a fit with the King model. There's this elevation in the surface brightness, so this is the surface brightness up here, at large radii. So this is the tidal radius here. And these are called extra tidal lights. Annalisa calls them extra King lights. But the Wilson model tends to fit this profile a little bit better, but it may be that these are actually, that this is due to the potential escapers. In addition, I mentioned this a little bit earlier, there's this flattening in the velocity dispersion at large radii. This is an in-body simulation by Globular et al. 2010. And if you just look at the bound stars, and this follows a profile that might be fit fairly well by a King model. However, at large radii, if you include all the stars within that truncation radius, then there's this sort of elevation and flattening of the velocity dispersion. So that's another thing that may be attributable to potential escapers. There are also, observationally, we see these high velocity stars that have a velocity that's larger than the escape speed of the cluster. And those could also be attributed to potential escapers. So there's a need for a model that would include these guys. So how do you actually build a snapshot model? Well, that's the challenging part. I know this is kind of dark and morose. It's like a graveyard or something. So the first thing you need to do is you need to compose a physically motivated distribution function. And that function needs to be a function of integrals of motion so that it satisfies the collisionless Boltzmann equation. And then, luckily, since we're doing a snapshot model, which means that it's time independent, we don't have to worry about this term here. Once we construct that distribution function, or make a first attempt at it, then we can plug it into, we can integrate over velocity space, and that should give us a density. You take the density, you plug it back into Poisson's equation, and you should get some sort of self-consistent potential coming out. And then you take that, plug it back in, and you do this iterative process until you get a distribution function that gives you moments in velocity space that describe the globular cluster profile fairly well, right? Hopefully very well. Okay, so that makes it sound easy, but how do you even identify potential escapers, right? How do we even write that into our distribution function? Well, luckily, Anon did a bit of an exploration of solutions to the restricted three-body problem in the Hills limit. So he identified two families of orbits, G3 and the F orbits, that are, the F orbits are stable, the G3 orbits are unstable or marginally stable, but they have an energy that is greater than this U tidal. I think I have an illustration. Okay, so those are the F orbits right here. These are stable. So we're going to care about those. And then the G3 orbits are these guys here. And we're going to also use those as a guide to begin this exploration. Now I just want to point out also that this vertical axis, earlier I said it was the energy, and I was kind of aligned, kind of not. It's related to the energy, but this is the Jacobi energy going in this direction. So the Jacobi energy, as it's written here, going negative has higher kinetic energy. I'm going to be referring to this a lot. So very small Jacobi energy, we're moving upward in this diagram. Low Jacobi energy residing down into the depths of that globular cluster. Okay. So in Anon's exploration in 1969, he identified several initial conditions for F orbits. So I plugged this in. He gave also the intervals of motion and the Jacobi interval as he used it in his problem. So he took those and I plugged them in. This is going from high gamma, reading across like this, to lower gamma. So remember, that's deep in the globular cluster. This is high kinetic energy. And use those to just see what these orbits look like. And they do, they are stable. And as you move toward very low Jacobi interval, then these actually look like epicycles of stars that you would normally see just orbiting around in the galaxy. So in the rotating frame, right, then you see these epicyclic motions. And these look like epicycles with their center, or their guiding center, in the middle of the globular cluster. But as you move up in Jacobi energy, these begin to close in on the tidal radius, which I've made this cyan color, and then cross over and look much more like Keplerian orbits around the center of the globular cluster. So, okay, that's a start. So now let's look at the G3 orbits. And I've circled this in purple here because I want you to notice that they're actually a little bit outside of this tidal radius right there. And they're also separate from what are considered stable orbits. So these are unstable here, this line here, and then moving up, they become marginally stable to unstable. But nonetheless, they're fun to look at. And they look like this. And actually, Ben, I was wondering last night after you left if these might be your fake escapers. So, so these G3 orbits, they're called G3 orbits because they cross this axis 3 times for every loop. And I don't know if you can see it from here, but up here in a very high gamma, that loop actually doesn't close. And if you follow these orbits any farther, then they just go way out. So then again, these out here, these look kind of like epicycles that are rocking, and then this looks like something completely different, like you have a twisted rubber band or something. But, so anyway, that's what the G3 orbits look like. And that's great and everything, but how do we fill in this parameter space, right? Because we don't just care about these orbits, we care about everything in between. We care about all the quasi-periodic orbits that are stable, that are going to behave like potential escapers and remain inside the globular cluster. So we, as a first attempt at this, we said, okay, well, these guys are stable, that's fine, but they're probably very, these orbits are probably not populated very well. So we're just going to ignore those for now. We're going to take everything from a gamma equals 0 down to what I call U tidal. And then we're going to take everything inside of the tidal radius, and we're going to try to see what we can do to fill this in. So when Anon did this exploration, he did it in 2D space or 4D phase space. But we want to really kind of fill in the 60 phase space though. So how does one do that? Well, this is how we started. So along this line here, these are just those G3 orbits again, but I followed them for 5 orbital periods instead of 1. So you'll notice that a lot of them, I don't know if you can see this very well on the screen, but they sort of fly off into space eventually. And then moving in this direction, I took the same gamma, so this is deep down in the cluster, this is high up away from the cluster in that Anon diagram. Moving in this direction, all I did was change the initial position. And then I found the velocity using the formula for gamma. And then I integrated using the equations of motion, and I get these orbits. And then I said, okay, following these for 5 orbits, I should be able to get at least a sense of what's stable and what's unstable. And the unstable orbits, instead of making these backgrounds like red or green, or like go or stop, because you couldn't see anything, I made them dusty rose and misty lavender green. And I know that Douglas is probably chuckling on the other side there, but so anyway, I have these orbits, I labeled them, and then once I know which ones are stable or unstable, then I can calculate intervals of motion. I mean, we already know what gamma is. The Jacobi interval is an interval of motion. And then I can calculate the angular momentum in the z direction and the total angular momentum, and hopefully use that as a guide for filling in the manifold that we're interested in. And then I did the same thing for F orbits. So these are stable again, right? Again, gamma going deep down into the cluster, coming back out. Except in this direction, rather than changing x, I've changed the inclination of the orbit. So each one of these by 15 degrees. When you get to 90 degrees, then that orbit, rather than being in the plane, is now up like this. And if it crosses like this, we would expect it to be unstable if it has an energy greater than u tidal, right? And the reason being is because the stable orbits are all retrograde orbits. They aren't prograde orbits. So this should be all red, which it is, until we get to energies that are actually inside the cluster, which is up here, and those are stable. And then there were some of these orbits that I wasn't very clear about, so rather than make them yellow or amber, I made them ivory because it's prettier. So that's these guys here. And then you'll notice, actually I'm going to go back a slide. So in these orbits here, moving across, we get these pretty rosettes, and then we approach something that looks like an F orbit, right? And that makes sense. That's what we use that for. Animations again. And then again, I can calculate these intervals of motion. So what do you do once you have this information? Well, you plot it. So I plotted gamma on this axis on both sides. This is the total angular momentum. This is the z-directional angular momentum. The x's and the pluses are various realizations moving across the plane. So where I started changing the x value, the initial x value, and then the circles represent when I change the inclination. So looking at this, so this is something like a Lindblad diagram. I don't want to actually say that it is a Lindblad diagram, because this is the Jacobi energy, it isn't the energy, which is what you would see in a true Lindblad diagram. So this green line, those are the F orbits, which is kind of interesting, because especially when you get close to the cluster, and you see this sort of like grouping of orbits, just to kind of orient you. So those are the sort of circular epicyclic ones. The red line, this is the angular momentum of the star, where I've assigned x to be the tidal radius, and then I've used gamma, so the Jacobi energy, to calculate the velocity, assuming the velocity is completely in the perpendicular direction to radial. So, so that turns out to really nicely fit that differentiation between stable and unstable orbits, where the unstable are now red instead of dusty rose. All right, and then this purple line on the bottom is what I'm calling a best fit, which means that I kind of look at it and eyeball it and try to put a line between all the dots. And we'll look at that later. Okay, so that's that diagram. And then looking at angular momentum, this is really tempting to use. Maybe I should go back to X. This is really tempting to use just because you see this really tight constraint, right, when you go up to high Jacobi interval. But the problem is that we see this overlap of orbits of red and yellow, and so it means that using this is not going to necessarily differentiate between the orbits. So, being the stable and the unstable orbits. So now using these two bounds, we can identify this region in the domain of gamma versus z-directional angular momentum And hopefully, that should describe the space within which we get we have potential escapers. So that's our initial theory. Let's test it. We did this with a Monte Carlo simulation. And we use this characterization of the potential escapers to, taking the time, to determine whether or not we get, this is a good description. So for the initial conditions, I just said, I want a random amplitude and radius, and it has to be less than the tidal radius as initial condition. And then assign some random direction. And then from that, we can derive the amplitude of the velocity from gamma, and then randomly select the angles and the direction of that velocity. Then I impose this restriction for the angular momentum given the gamma that I've used, and I use that and I say, okay, go integrate the orbits for several orbital periods, and if the radius ever exceeds the tidal radius, then I flag it as bad. This tells us, so I did this is for 1,000 realizations per gamma. And then it looks like this is pretty nicely describes the potential escapers if you're close to the cluster in energy space, right? So these are the ones that have just a little bit more energy than the tidal, right, energy. But then as we move away, this gets pretty ugly. So what's going on? I mean, first of all, I'm going to go back a slide again. This parameter space is very, we explored it. It was limited, our exploration, I should say. So maybe there's something we're not picking up on. So then this is a heat map of the same thing. We're looking at, or the Lindblad diagram. So this is gamma, this is z-directional angular momentum, and these dots are red if it's bad, and they're blue if it's good, and and this is the realization in this space of the exact same simulations. And over here, there's a little bit of elevation in terms of the flat ones, which we kind of expect because this is edgy, and I look at these orbits and they are a little bit unstable.
What are the colors?
Oh, so if it's blue,
Yeah.
that means that I've totally, this is a very good description of the potential escapers. When it gets red, it means that it's a poor description. Right? So there's a little bit of elevation over here, and I'm kind of okay with that because part of it is that there's the sampling is low over here, and the interpolator sort of is a linear interpolator, so it's sort of elevated it here a little bit more than maybe you would expect. But down here, this is pretty ugly. So what this tells me then is that probably my best fit line wasn't the best fit, and I need to change that. So the line, if you remember before, was something like this, so I need to go like that. And hopefully that'll sort of solve that problem. Okay, so now I'm putting that on the back burner because we only had 5 weeks. And we selected this sort of subregion here that we're interested in exploring. So in there, what I really want to point out though is that this line here represents the minimum in the angular momentum, and then I'm making the maximum at the angular momentum 0, and that gamma is going between 4 and 2.5. So now I'm going to make a first attempt at writing down the density. So the distribution function initially, we just assumed it's constant. That's the nice, it's a good starting point anyway. I had to convert velocity space into gamma, or Jacobi integral, and z-directional angular momentum, so we get this little term out here, and then I have these limits on the integral. That is u tidal, and this is described, that's what describes that line, that red line in the Lindblad diagram. I'm just putting this up as a reminder that that's what gamma is. And then I calculated that integral, which is super, super easy, and I get all these constants over R. So what that says is that the density goes to infinity at 0. So something's awry. And we realized that we lacked a condition on the potential. So that's sort of absorbed into the Jacobi integral and the way that we've written it, but I just need to make a bunch of transformations and try to get that work in there explicitly. Fun stuff late at night. All right. So in the future, I need to improve this distribution function. You know, first of all, I need to include the potential. I need to make that conversion I just talked about. I need to, and then after that, I'm going to do exactly the process that I said before. Take that density, plug it into a Poisson solver, and then loop through until I find moments of that distribution function that are well fit to observational and numerical data, so that we have a fully self-consistent model of globular clusters that are that include the potential escapers. So I'm running out of time, so I'll leave my conclusions or summary up. Is it that boring?
Where you had your sort of heat plots with blue and red regions, you had a heat plot with blue and red regions showing where your identification of potential escapers was good and bad.
Yeah.
I'm confused. What's the lines and dots which are on top of that?
Those are the actual sample points, and they're flagged red if they are unstable, and they're flagged blue if they're stable.
Okay, so the region on the left, the sort of green, as you said, is
Yeah.
not great. How do you know that that's not very
That that's real or not real?
How do you know that your characterization of orbits is stable versus unstable isn't very accurate in that region if you have no sample boxes?
Well, actually, this region is outside the line anyway, so that I drew. So this is actually, this should be an unstable region. It's just that it should have been excluded. So the interpolator built in this sort of slope upward just because it's for the sample.
Okay.
So when this is actually, I mean, this is something we really did explore more extensively than what I'm showing you. But if I don't put those cuts in, then yeah, this becomes a dark red region, right? This is an unstable region. This is an unstable region. But in theory, if the bounds that I put on the box are good, then this should all be deep blue. Right? Does that make sense?
Yes. Thank you.
Yeah.
I have a question related to one of the very first slides where you looked at the difference between the sleeping model and the actual data. I don't know if it was the sleeping model. Yeah, that one.
That one?
No, the next one.
This
Yeah.
one.
So, how do you learn that these extra points that are above the line are genuine potential escapers, rather than just being stars that are escaping properly?
Right.
Because they're escaping velocities so small, they just hang around.
Right, and I think that's a legitimate question, right? And and also, you know, the Wilson model, like I mentioned here, actually does fit these a little bit better anyway. So I can't really answer your question other than to say that in n-body simulations, I do believe anyway that these stars on the outskirts are bound, and they also give, you see them in excess velocity dispersion in the outer regions. Although being bound meaning they're stable in stable orbits, not bound in terms of energy bound.
The blue one